Thank you for coming. I'm glad to share some of my previous study in my PhD study, and because they are directly related to my current work here. And the collaborators are my supervisor and my PhD supervisor who is a PhD student of Yale, and also other people from the addition. And before starting my slides, I will follow Pierre's style to introduce my life, because I found it's a very efficient way to find some good friend and make it easier to enjoy the life in France. So if you cannot find me in the office, I may be drawing pictures and practice Chinese operas or dancing and chatting with ChatGPT. Oh, I'm so glad that a guy come, because he think there is no seminar and feels so happy, and unfortunately there is one. So, and thank you to come as you come. This is ChatGPT and this is me, because I found that ChatGPT is like a battery and makes everything so easy and save a lot of energy. And this is a picture drawn by ChatGPT. So I'll go back to the boring science. This is the outline. First, I will introduce the back projection method and the two applications. And the third application is to use stats data and some future work. Back projection method is to check the rupture fronts of a large earthquake. How it works. The seismograms recorded by a dense array will look very beautiful and simple in teleseismic distance. So you can use cross correlation to measure the travel time difference, and then use it to locate the subsources of a large earthquake. And only the direct peer arrivals looks very coherent, and the coda waves were less coherent. In this way, you can detect and locate the subsources in a large earthquake. And the advantage is that it can use a very high frequency band signal, so it has very high resolution to describe the rupture process of a large earthquake. And so that it can provide a lot of insight for fault mechanics. For example, this is the 2012 magnitude 8 of Sumatra earthquake. And this is a back projection result. And you can simplify this result to a cartoon like this. So it's this earthquake rupture from the epicenter and reaches an intersection. And then it branches into two branches. And then there are a lot of surprising phenomena in this earthquake. Without this very high resolution method, it's very hard to observe these details. Another advantage is that it is very stable method, because it needs very few parameters. So you can use it to issue a warning, because it can be automatic very easily. So that's my work in the first 3 months in Geoazur. I mentioned that the waveform in teleseismic distance is very simple. For example, this is the Australian array, so that all the source in this ring within 30 to 90 degrees from the epicenter from the array can be all earthquake region within this region can be imaged using this array. And we have 4 other arrays, and from each of these arrays, we can get a result, and then we can compare the result to increase our confidence. And this is how the automatic back projection works. This is the manual result, and this is the automatic result for the magnitude 7.8 Tokyo earthquake in the last year. And this is the location. All the dots are like the subsources of or the high frequency radiation location. And this is the distance along strike, and this is the time. So you can estimate the rupture speed and how the direction changes, it becomes whether it becomes two branches or one. And this is automatic back projection result. And at the same time, we can estimate the uncertainties. So within 2 hours, we can get the result, and within about 8 hours, we can get this uncertainty, including the rupture front. Using this information, we can constrain the slip inversion better. So you can see there are some very large uncertainties here, which is about 50 kilometers, and here, which is about maybe 10 kilometers. That means that for a magnitude 7 or 6 earthquake, we don't have the confidence to explain the details because the uncertainty is so large. And for even smaller earthquake, it looks like a point source. So what we can do to increase this resolution, so this is the equation between the resolution of the wave projection and the parameters of an array. So to increase the resolution further, you can either decrease the epicenter distance to use local stations, or you can use higher frequency band, or you can use a larger array. This is challenging because the higher frequency, you are using the lower coherence. So the result will be very unstable. The motivation of my PhD thesis is to develop a local array back projection. It's challenging, so that's why it become my PhD thesis, because it's challenging. The motivation, the first one is high resolution, and there is a second motivation that is faster, because you need less time to collect the data. So we mentioned that it's challenging because you have multiple phases. The waveform is more complicated, more sensitive to the local velocity structure. So to solve these problems, we use some very simple method, like divide the whole stations to several fan-shaped sub-arrays and combine the result to increase the stability. And also we select the stations carefully and figure out which stations are more coherent. And we also apply empirical calibration to the velocity structure to make the result more accurate and concentrated. So it works for the Southern California network because it's very dense. So we can image a magnitude 6.4 ridge-crest earthquake. So without this method, this earthquake will look like a point source using from the tiny seismic distance. So from here, we can roughly see that the earthquake rupture this branch first and then transit to this branch. And another motivation is to build some early warning system. So here is the application to the Tohoku earthquake using the HiNet and KNet networks. And this is the result of the back projection. This very light color is the location of the low frequency radiation, because tsunami is more related to the low frequency period. And after we get the result, we build a very simplified steep model for predict the tsunami waves. And this is the comparison between the recording the tsunami waves and the recording. And using this method, we need 3 minutes. The earthquake duration takes about 3 minutes, and the waveform propagation from the epicenter to the farthest stations takes about 2 minutes. And the data processing, most are spent on the forward simulation of tsunami waves, takes about 2 minutes. And in total, we need 7 minutes. So this is the, when we use this system, then this is the blind zone. And along the coast, you have at least 20 minutes to escape. But this is only works for Japan, maybe because for other regions like Sumatra or Chile, one problem is that the coast seismic region is just below the coast. The coast seismic region are very close because the change is closer compared to other regions. For example, this point, coast seismically, there is a large subsidence about 3 meters seismically, and so for this region, it's in the blind zone according to the define of the blind zone. But still, you can do something because the tsunami will not come so fast because the ocean layer will seismically will subsidence with the land simultaneously. And after the peak of the tsunami come, then it's the real hazard come. So you can use this time to issue the warning and to escape. But there is no so much time compared to the Japan in Chile, because you can see this tsunami wave propagation snapshots within about 8 minutes, the peak almost reached the coast. It means we need to do everything, including the collection of the data and the data processing and escape within these 8 minutes if we want to help people to escape from the tsunami hazard. So I think that's one of the motivation in the ABYSS project, because this the theta in ocean bottom or the which is closer to the change and has very high density, so it could improve the current warning system in Chile, because the seismometers are very sparse here. So this data set looks perfect for our method, because first, echo is free, but in fact, I know the integrator takes a lot of money compared to for an individual research group. But I think compared to the government, it may be reasonable, and it has large coverage. For example, here you have about 1,000 kilometers cable. If it can roughly cover all the subduction zone here, and you have the large chance to catch all the subduction large earthquakes. And it has large density, so the sensor gap is about 4 meters. That will guarantee a higher resolution, because we see that if you have a smaller station gap, then you have very high coherence and high frequency, so you have very high resolution. And also you have very large, very long cable. So this aperture of the array, the size of the array will also be very large. So this data set looks perfect. But still you have some challenges. For example, the scattering problem is very severe in the ocean bottom, because the sedimentary layer has a lot of and also the linear geometry makes it challenging to locate earthquake. And also the saturation problem is not solved very well. But I'm so lucky that I come here, so we have so many experts, experience, and techniques to deal with all the challenges. So this segment is what we are using to do our experiment. This is a previous exploration about whether the seismic informing method or the back projection can be used in that data. And they found the important conclusion, that is, if you integrate from the original stream rate recording to the particle velocity, the waveform will look much more coherent. So that means your back projection result will be much more stable. But at that time, they argue that you need the perfect coupling and you need a co-located seismic station. That's not possible for example, for the ABYSS project cable, because the coupling is changing everywhere. Only when you install the cable very carefully, and you can get this perfect coupling. So Alice said, "Don't worry, please use my product, the integration method, the local integration method." So using this method, you don't need any seismometers. You don't need a perfect coupling. You can get still the best integration result as possible. So this method can roughly solve the problem about coherence. But you still notice that compared to this theoretical arrival, the recorded S arrival has very large bias. And as the came again and said, please use my second product, the sedimentary correction. And it's a very recently developed method, and it works perfect for my purpose. After this correction, the arrival looks much closer to the theoretical S arrival. So this is because this correction is mainly related to the thickness of the sedimentary layer. It's almost constant for all the earthquakes. So you can just measure this delay and then apply it to all the earthquakes. So using the waveform after this processing, I just use similar method as what I introduced previously to divide all the cable into several segments and apply bifurcation to each of them and then combine. Then I get a result like this. So this is the this is the waveform from this segment, and this black curve are the recordings after the pre-processing, and the red lines are the synthetic waveforms as a comparison. So you can see very clearly how the travel time change and the signal to noise ratio for this S arrival. And this is the comparison between the synthetic test and the recorded data for this for magnitude 2 earthquake located here. This star is the epicenter, either the input in this synthetic test or the relocated result. And the background, you can see it as the probability of the source location. So we can see that the recorded data gives us a similar result as a synthetic test, which has a resolution about 4 kilometers. That's much better than the traditional data set and traditional method. And this method is very preliminary. We have a lot of other things we can do to increase the resolution further. How about other locations? We only did a synthetic test and recording here. And so we also did want to explore other regions. So we did a similar synthetic test for all the surrounding regions and plot this resolution distribution. And we found that around these two regions, we have relatively higher resolution. This is related to the geometry of this cable. And we also add some disruption to the velocity, and we calculate how large is the location bias, and we found within these regions, the location error is relatively smaller. So we define this region as a high resolution, high robustness region, and we propose to apply the bifurcation within this region if we don't apply any calibration about the velocity. Because you will have very large bias and lower resolution outside of this region. And we can imagine that if we have longer cable, this region will also extend accordingly, assuming that the signal to noise ratio is high enough. That's a problem. And this is how it works for the real recordings at different locations. And we can see that with these very center locations, compared to the synthetic test, the point sources are imaged very clearly. And at the regions that are far away from the center, there is large trade-off. And especially when it in this region, there is multiple peaks, so you don't know which one is the correct one. That's because it's too sensitive to the velocity model. And also very large trade-off, so you need more constraint from different direction if you have more. So you need a longer cable to cover that region. So the real strength of the back projection is to image the rupture process of a large earthquake. So we pick some point source here, which is shown by these magenta stars as empirical growth function events, and then we generate this synthetic test for our magnitude 7 earthquake. And we can see these are the input location of the subsources, and this background is how it's the result of the back projection. And we can see that both the locations and the time is resolved very well compared to the input. But this result is based on a perfect calibration about velocity. You can see that these arrivals of each sub-event are very smooth. That's because we align the empirical growth function for each event. In the real case, the alignment cannot be done individually for each subsource because they are mixed with Koda waves. We can only predict the travel time error and remove them, or we can apply some inversion and or calibration empirically. So that's the next step. So now we come to the conclusion. So in part 1, we develop a method using local seismic arrays to image large earthquake, and has higher resolution and is faster, but limited to regions with high density stations like Japan and Southern California. And then we have extended this method to the DAS data, so we can use 2 more regions, including Chile. And in this part, we find a high resolution, high robustness zone, and we can have a resolution about 4 kilometers. And this method works well for synthetic large earthquake if velocity structure is accurate enough. So that's our future work. And thank you.
So thank you. Do you have any questions?